All right, welcome back, everybody. So last time we talked about this would be section 5.3 in the text, but we gave it the projection perspective. So we started talking about the closest point problem as being a projection on an orthogonal projection onto some subspace of an inner product space. And as we looked at that problem, we were able to formulate the closest point problem from an abstract inner product space as a problem about a standard Euclidean inner product space. So even though we were talking about an abstract general approach or an abstract general problem, we were able to kind of use a basis to put our question back into Rn for some n and some matrix A. And the question did come down to, can we still minimize this square distance formula, or can we minimize the square distance expression between what we can reach versus how far away this other vector b is from the subspace that we care about. And well, I will remind you that Graham-Schmidt gives us a way to factor A, this matrix A, so that we can talk about an orthonormal basis for that subspace that we want to project onto. And this will give us a very specific basis for the subset, but all the same, it's going to be a really convenient basis for us in the sense of projections. So whatever basis we want, this beta in the abstract inner product space can be transformed via this Q matrix into some nice standard orthonormal basis, or the standard orthonormal basis for Rn with the standard dot product. So the problem of us solving these closest point problems, these minimization problems in abstract inner product spaces, as long as they're finite dimensional, it suffices for us to fully understand the problem in Rn, right? Because we can go ahead and transform any problem in the abstract inner product space into a Euclidean problem. And that's what this section 5.4 is going to be talking about. We're going to be looking into solving that problem completely in Rn, right? Just figure out what it looks like in Rn, and you can always translate the problem in the abstract inner product space to Rn, solve it there, and then transform back to figure out what it looks like in that abstract inner product space. So what we would like to do here is first define what the problem is in Rn. So we would like to find what is called a least squares solution to the linear equation ax equals b, right? So it's our usual setup. A is an arbitrary rectangular matrix. X belongs to Rn and b belongs to Rm. And a least squares solution to that equation is any vector x star that minimizes the square Euclidean distance, right? It is that same capital D function that we've been minimizing for the past few videos. And we are minimizing this over the subspace Rn, right? We're doing this over the entire vector space Rn, right? And there are a couple of different cases to consider, one of which is very boring in one sense. And that is, if this linear system actually has a solution, well, I mean, that's going to be the case where B belongs to the image of that matrix A. So that means that there is at least one solution, right? We don't know anything about the kernel of this matrix necessarily. If the kernel is trivial, then we will get a unique solution, but it's entirely possible that we have a non-trivial kernel and will therefore have an affine space's worth of solutions to this equation. But usually for least squares problems, we want to make sure that we get a unique solution. We want exactly one answer to this problem, and we discussed that earlier, or toward the end of chapter 4, and that would usually be our solution x star that belongs to the co-image of the matrix A. But we have solved that problem. So the more interesting case for us is what happens when this ax equals b equation actually doesn't have a solution, right? When b doesn't belong to the image of that matrix A. So what we're going to do is identify this subspace W as being the image of the matrix A, and this gives us the same setup that we had from before when we were talking about the closest point problem. So we found through projections, right, putting this guy in the projector form, that the Gram matrix A transpose A can be taken to be K, and F can be taken to be the projection of B onto the image of A. So that would be A transform, or not A transform, A transpose times B. Right, so if K inverse exists, right, this would be the case where K is a positive or just a definite matrix, or at least it has a trivial kernel. If that inverse exists, then X star, right, the thing that I'm trying to find, the least squares, or not least square, the solution that I'm trying to find, X star, is equal to K inverse times F. And we showed that this is the closest point, and it is unique, right? So I can say the closest point in W to the vector B. So actually, it should be, is the unique closest point, actually, so unique should be the least norm vector in W. Yep. Least, so that would actually belong to the pre-image, so that's not actually in W. Right, so this would be the least norm solution, perhaps. And that would mean that AX star is the unique closest point. And then we continue in W to B. Right, it looks like I had a little mistake in there about where X belonged. X belongs to the domain, right? So that would be somewhere, that would be in Rn, as opposed to vectors in W that are vectors of Rm. So do be careful. I was a little sloppy there, so my apologies. So to reiterate, so if we take the Gram matrix A transpose A to be K, and our linear components F to be the projection of B onto the image of A, so onto W, then if that K inverse exists, right? So if this is a definite matrix, then X star equals K inverse times F will be the least norm solution, and A times X star is the unique closest point in W, which is the image of A, to the vector B. Right, so the way that we can guarantee that K inverse exists is if the kernel of A is 0, right? It's the trivial space. All that means is that the columns of the matrix A are linearly independent. So that's enough to satisfy the existence of, or to, that is sufficient for the inverse K inverse to exist. We then have the following theorem, that if we have a matrix A in a rectangular matrix A with real entries such that the kernel is trivial, then the least squares solution X star does exist. It is unique, and it solves what are called the normal equations, which we outlined a little bit very briefly last time. That I have A transpose A times X has to equal A transpose times B. So what we are doing is we are projecting B onto W. So W, remember, is the image space of A. Therefore, if we project onto the image, then there is a solution, right? But this comes at the cost of us changing what the matrix on the left-hand side looks like. This will be A transpose times A times X rather than just a plain old A times X. So we are, in fact, smushing this problem down so all the action occurs on the image space. Right? And then the least squares error is going to be defined to be, well, how far off in the image space we are from hitting that vector B. And we're going to go ahead and call that a square. Right? So it's an error of squares. And based on our theorems from before, our minimization principle, we can say exactly what, we can say that there's a couple of different forms that this least squares error can take. Now it's either the square distance from ax star to b, or if we expand this out, we can see it as this big equation down here. So norm of b minus this gigantic expression, but it's all in terms of a. Or I can do this in terms of b and f. All right? So there are lots of ways for me to express that least squares error. And we move on, and this would actually be a great place for us to do an example. So let's say that we are given a collection of data points, right? If you've taken statistics, this will look very familiar to you. What we are going to create here is what's called a linear regression for the data points. Now, when we compute linear regressions, oftentimes, not all the time, but oftentimes we say that the line of best fit for the data, right? A line that best approximates the way that the data is clustered, or the way that the data is oriented. We're usually looking at lines that minimize how far the line is in vertical directions, right? We're taking all the distances from the line, or from the line to the data. And notice these are all vertical distances, right? I'm not projecting my points onto the line, so do be very careful in noticing how we measure that. But the data is now going to be a certain distance away from this line. And what we're trying to do is minimize how long those red lines are, right? The total length between all 6 of the data points and the dashed blue line. So our goal here would be to find coefficients alpha and beta that minimize exactly that, where we're trying to figure out how far or how good this blue line is to approximating the data. And we have an objective way of measuring that rather than just kind of eyeballing it and saying, yeah, that's good. So in order to set this up, we are going to look at each one of these data points in turn and ask, what should this look like if it's going to lie on some line? And that's exactly what we're doing here. If we say that our data fits this particular profile, that it looks like alpha plus beta times t, then what we're going to do is start with the first data point and say, okay, if I plug in t equals 1 and, t equals 1 and yi equals 3, then this point is on the line. It's on whatever this line has to be. So alpha plus beta would have to be 3. Now we can play the same game with other points as well. So go to, not the first data point, but go to the second one now. And that would be what happens if I plug in t equals 2 and y equals 1. So alpha plus 2 beta would then have to equal 1 as well. Now, we know that if we just have these 2 points, then there is exactly one line between them, and we could actually see that in the diagram over here. There would be just one line between x1 and x2 as the points in my data set. But we have multiple points here, and that's where we run into trouble, because we are now over-determining this collection of points. And you can see these data points do not create a line between them, right? They can make pairwise lines, but they together will not sit on a single line, right? They are not collinear. So this is the problem. Our solution now does not exist. So the best thing we can hope for is to look for a least squares solution. And we do this with the remaining 3 data points as well. So we get a 4, 4, a 5, 8, and a 6, 6 as the remaining 3 data points. And we still want to figure out which alpha and beta are kind of best suited to creating that line, or a line that is best approximates the data. And this we can simplify in a matrix system as an AX equals B problem. So let's continue. So again, when there are 2 data points, there's always a solution. Well, the only problem is if the 2 points are stacked one on top of another. But at that point, we wouldn't have a function anymore, so our model doesn't make any sense there. Any other case is essentially guaranteed to not have a solution. Basically, if the number of data points exceeds the number of coefficients that you're trying to fit to, then you're almost guaranteed to not have a solution. So we're going to look for a least square solution to ax equals y. And we can check. The kernel is going to be non-trivial, right? The kernel of the matrix A, which, by the way, this guy has a name. Oh, this is a Vandermonde matrix. And I'll show you what that looks like in MATLAB. But this is a Vandermonde matrix. Right, and this is what you come up with when you try to fit data to a polynomial regression. Right, so we can do that. But maybe an observation is that the only way that our kernel is non-trivial is if there are two rows that would be identical in this case. And that would mean that we would have to have data taken at the same value of t, which would mean the two data points in our list here would be stacked on top of one another, and that is not going to create a function. So we are going to avoid that by assuming that our data only takes on points at distinct times, and this creates something called a time series. So the data up on top here, this is a time series. Yeah, there we go. All right, so since our data is a time series, we don't have this problem, and we know that our data, or our Vandermonde matrix, has a trivial kernel. It means that the two vectors here are linearly independent, the columns of A are linearly independent, and we proceed. We can define an error vector as essentially the least squares error to the problem. So to minimize this squared error, we're going to solve the normal equations, right? So this came from A transpose A times X star equals A transpose times Y. So because the kernel of A is trivial, we have an inverse to this A transpose A, which, by the way, yeah, it is a square matrix, kind of a fun thing to think about. And we wind up with the least squares solution in that way. So we can actually do this explicitly for this problem and see that A transpose A is equal to this matrix. And you see that Gram matrix is going to be positive definite, and we can project Y onto the image space there, and it looks like this. So the normal equations then turn out to be what happens when we solve A transpose A augmented against 29 by 118. And A, or alpha here, will have to be 23/15, and beta will have to be 33/15. Right, so what that is exactly, we're actually going to see this in MATLAB just in a moment. But the point is that this set of coefficients gives us the line of best fit with respect to the squared error E. So this is the solution that minimizes the total error, right? And I can compute this by hand pretty easily, right? So there's 19.276 as the square error, and that will be the minimum square error for this problem. So among all lines that I could have picked to fit the data, this is the one that has the smallest error, and that square error is 19.276 or thereabouts. And statisticians, if you're wondering what happens, like what the relation is between a correlation coefficient, we're not going to go ahead and compute that just yet. We can save that for chapter 8 when we start talking about principal component analysis, but we will talk about it, so hang with me. Otherwise, I've set this up in MATLAB Mobile, so let's have a quick look. And I might have to turn this back on, so session expired, please reconnect, thank you, la 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 la, connecting to the cloud. And I set this up before, so I've already entered in what the vectors, it'll be, there we go. The t vector is 1, 2, 3, 4, 5, 6, and the y vector, right? So together, t and y, these are going to be not our matrix A, but they are going to give us the points. So each row is going to be a data point. So the first row is x1 from the example, so 1 by 3, 2 by 1, 3 by 7, and so on. What we're going to do here is actually compute this in two different ways. First, let's see. So we can compute the Vandermonde matrix for the vector t. And this actually sets it up a little bit backwards. So I usually build my polynomials from constant terms up to highest order terms. MATLAB builds this the other way around, where it goes from highest terms down to the constant term of the regression polynomial. But what I want you to focus on are the last two columns here. So A, I'm going to make a 0 matrix, and this is going to be the length of t by 2. I'm going to make 2 columns here, just like in our example. So A, and I'm going to use all the rows of, and we'll do number 5 here. This is going to be I should say little a equals Vandermonde of t, so it's that matrix. The first column of A is going to be the 5th column. Is that right? Do I want the 5th column? No, we're going to make the 6th column so we match our data from before. Yep, so there's 1, the column of all ones. And big A2 is going to be the 5th column of little a, 5th column of that Vandermonde matrix. So we've just reordered the columns, that's all. And the vector y here is what we're going to throw on the other side. So what we would like to do is solve A transpose A against A transpose times y. And what do you think we're going to get? That sure looks like, what was it? It's 21 over 15, 23 over 15. There it is, 23 over 15. So yeah, 23 over 15, sure enough, there's the 1.53333. And then we also had a 33 over 35, did I say that right? Yeah, 942.9. So this is exactly what we got from before. So I'm gonna go ahead and label this guy coefficients of, or coefficients will be, yeah, A transpose A backslash A transpose times y. So there are my coefficients. So alpha is going to be the first coefficient, beta will be the second, and I can create this big vector, big Y, and I'm going to go ahead and say that big Y is going to be paired with all of these approximate points. So big Y is going to be A, and it should be, yeah, so coefficient here, that's a column, yeah, so big Y is going to be A times the coefficient vector. There we go. So I can go ahead and plot this. X by Y, I'm going to go ahead and put this in red and make little circles. Oh, need one more apostrophe, sorry, there we go. And have a look here, I can go ahead and now see all of my data points. Right? So this is effectively a scatter plot of my data. And if I wanted to see what my approximation looked like, I'll plot little x by big Y, and I'll put this one in blue so they can see it better. And have a look. This is going to be the line of best fit. It is minimizing the vertical distance between each of the red points and the blue curve. And if you don't believe me, well, let's have a quick look. A times, or big Y minus little y, I would like the square norm of that. And I should actually square it, right? So square norm. There's the 19.2762 that we saw in the example. The claim is that that guy was the least error, or the smallest square error, and that is based on our theory. We can actually verify this a different way. There's a function in MATLAB called Polyfit. And Polyfit is effectively going to create an interpolating polynomial when possible. So it's going to try to fit a polynomial of whatever degree you want to your data. So if I recreate a coefficient here, maybe I'll do this as coefficient poly. This is going to be polyfit x, y, and I want to do this to a linear polynomial. So voila, I wind up with the 0.9429 again and the 1.5333. But notice that they're given in now descending power order. So the 0.9429 is going to correspond to the t, and the 1.5333 is going to be the constant term. So what I can do here is create a polynomial by creating a 0 vector, and this is going to be zeros that are going to be the same size as, what will you be? You'll be the same size as big Y. So what I'm going to do is create, in general this will be a for loop, but yeah, actually we can do that. For I equals 1 to the length of coefficient, right, the coefficient poly, I'm going to go ahead and say that my polynomial poly is equal to whatever it was before plus a new coefficient tacked on. So coefficient poly I times, what will this be? This will be little x to the power of whatever length of coefficient poly is minus II. So this is a linear polynomial, so the length of coefficient poly is 2, and I'm subtracting 1 on the first step, so that'll be the linear component. And I'll subtract 2 on the second part, so that will be the constant component. So what can I do here? Plot x with poly, and sure enough, that's going to get me my line again. And I can plot that against data, so you can see I'm not just blowing smoke up your butt. There's R0 and x with poly. I'll do that in blue. And this gives me the exact same interpolating polynomial. So I can actually check how far apart is, poly minus big Y. Turns out those are numerically, like they are the same approximations. They go about it in a slightly different way. So there are 2 different ways to figure out your least squares solutions. But let's say that we didn't have our line from before. We actually could set up our normal equations, say for a square, like a quadratic approximation or a cubic approximation. So let's do a quadratic approximation. Coefficient poly is now going to be polyfit x and y, but we're going to do this, I don't know, quadratic? Let's do cubic. Let's do a cubic fit. So we're going to go to 3rd degree, so we have 4 coefficients here. Poly is going to once again be zeros, and it will be of the same size as the big Y that we computed before, or I suppose it would just be the size of little y. It's the same thing. But we'll create that for loop to length of poly, or this would be to length of coefficient, I suppose, coefficient poly. Whoop. And we're going to run the same scheme. So poly equals what it was before, plus coefficient II times x dot caret, and this will be length of coefficient poly, and we're going to subtract off II at each step, end that loop. Oh, coefficient poly. What didn't it like? Poly, so, oh, I didn't say coefficient poly, that's what happened. So we'll do that, and then we'll change this guy is the problem. Shame on me. There we go. And now that's good. So poly now is going to be a bigger coefficient here, or it's going to be a bigger guy. Did I do, oh, I didn't zero it out before. Yeah, that looked a little big. Poly equals zeros, and again, size of y. So we're just going to redo this, so bear with me. Size of y. So we get that guy. So 1, 2, 3, 4, 5. All right, you know what, screw it. For I equals 1 to length, coefficient poly. Then we go up and just create that line. End. There we go. So poly. There we go. That looks better. So check how close that is to the original y vector. We can actually plot this. X, y, and we'll do that in red circles again. And then we'll do x with poly to get our quadratic approximation. We'll do that in blue. And lo and behold, we have a cubic approximation to our data. Right, and it's approximate, it's not truly interpolated until I do something like well, until I change it up so that I have more data points in between the data, or I put more refinement in between the data points. But this is the cubic function that best approximates our data from a least squares sense. So it looks like it's long in certain places, but if we tried to make it closer to those points, we would actually incur more length in different away from different other points. So we can do this in MATLAB. We can do this by hand, and I hope you can do both. I hope you ask questions if you have trouble doing either of these. But this is one of the primary uses of least squares approximations, or least squares problems. You can actually fit these to splines as well, so you're setting up a whole mess of these normal equations. But that is used in computer-aided design a lot for engineering. Cubic splines and Bezier curves are actually a very close relative to this problem. But yeah, I think that might be just about all that we're going to talk about for these solutions, or for these for this kind of application. But you're welcome to look into them more. There's an entire section in your textbook that talks about them. And there's even an application into how you create, let's see, what would it be? Typesetting, how you could create your own fonts if you wanted. And I think that's kind of an interesting application here, especially for computer-aided design. So let's go ahead and kill the video here, and we will come back for one last thing out of Chapter 5 here, and we're almost out of Chapter 5. So the last thing we'll talk about is the discrete Fourier transform. And next time we'll begin with an example of when or how this shows up and how we might